So welcome to Equilibrium Part 3. We're going to cover the last part of this chapter in this section, and we are going to do a little bit of calculations just because I want you to see all the various ways that we can solve equilibrium problems, whether depending upon what we're given initially up front. Here are our objectives. So we're going to look for a shortcut, which everybody wants, right? So we're going to determine when you can use this XSmall approximation. We're going to look beyond systems that are at equilibrium and what happens to systems when you stress at equilibrium. This is called Le Chatelier's principle. And this happens a lot in equilibrium scenarios where you change a concentration, you add temperature, you maybe decrease the volume of a gas. That's going to temporarily affect that reaction. It's going to make that reaction either go forward or reverse. And then that reaction is eventually going to come back to equilibrium. So we're going to look at those stressors and predicting the equilibrium shifts that happen. All right, so I want to review what's happening in these various equilibrium scenarios. So the problem with this is, one, the math is a little bit complicated because you may or may not be doing a quadratic equation solving. And two, it's hard to figure out which calculation to use, how to approach the problem. So there's four main ways to approach these problems. And it really depends on the information that you're given up front. And so I'm just going to go through these really quickly with you and do some simple calculations with you to show you what I'm talking about. So we actually have five different ways. So the first one is the simplest, and this is I want to find the equilibrium constant, KEQ, if I know all equilibrium concentrations of reactants and products are given. This is my simplest way to look at this scenario because I have everything given to me. So let's say I have this simple equation, and I'm going to write my mass action. So once I get these concentrations here, I can plug it in and solve. And remember, these are all equilibrium concentrations. Right? These are not my initial starting concentrations. The other piece of information that you're given is you're given these values, all the equilibrium concentration values. So now all I need to do is just plug in my values and solve. So KEQ equals, that's going to give me a value of 6.6. So this is kind of the simplest. I want to find KEQ and all my equilibrium concentrations are given to me. So that would be one type of problem. The second type would be if I want to find EQ, so I want to find my equilibrium constant, and I know all my initial concentrations are given to me, and one equilibrium concentration. Doesn't matter which one, as long as one of the substances, one of the equilibrium concentrations were given. Okay, so now I have all my initial concentrations and one equilibrium concentration. So I'm going to go back to my problem. I'm going to write my mass action, which is the same because this is the same equation. Again, these are all my concentrations at equilibrium. And now I'm going to give you my initial concentrations here. So I don't have any initial starting concentration of C, and my equilibrium concentration of A is 1.5 molar. So in this scenario, I'm going to check to make sure that there's no initial concentration of a product. If so, I need to calculate Q and determine reaction direction, and we'll come back to an example of that. But since it's 0, then I don't have to worry about that. And I'm going to set up an ICE table. So I wrote my law of mass action. Now I'm going to set up an ICE table to track what my changes are. My initial concentrations, my change, and my equilibrium. My changes here, what's changing is this is going to go down by some amount. This is going to go down by the same amount because this is a 1-to-1 ratio, and this is going to go up by 2 times that amount. So now my equilibrium concentrations are going to be 1 minus x, 1.2 minus x, and just 2x. So now I'm going to substitute these back into my mass action. So the second was write an ICE table. 3, substitute all my values into my mass action. And before I do that, I'm going to calculate x. And I can calculate x because I have this little gem right here. So I know that at equilibrium, A is 0.15 molar. So that means this whole thing here equals 0.15 molar. So I can solve for X. So 1 minus X equals 0.15 molar. That means X is 0.85 molar. So having found that out, then I can substitute that in and find these two here. So this would be 1.2 minus 0.85 molar, and this would be just 2 times 0.85 molar. And these are going to give me my equilibrium values. So this becomes 0.35 molar, and this becomes 1.7 molar. So now I'm going to plug those values in back into here. So KEQ equals 1.7 squared over 0.15 times 0.35. And then that's going to give me a KEQ value of 39. So that's the second way, is I have all initial concentrations and one equilibrium concentration. I'm going to set up an ICE table, but I'm not going to need to solve a quadratic because I have one of my equilibrium concentrations, so I'm going to backtrack to find X from there. So this is a little bit more complex. So in the complexity scale, this is more complex, but not terribly complex yet. Our third way is I'm going to look at the relationship between Kc and Kp. And so remember, Kp equals Kc RT delta N. So if I have Kc, I can find Kp, and vice versa. If delta N is 0, then Kp equals Kc. So if I go back to my problem that I had, and let's say these are all in the gas phase, and I know that my Kc value from my previous one was 39, and I want to find Kp, I'm just going to plug it into this equation here. So first off, I'm going to find delta N. And delta N is the number of moles of product minus the number of moles of reactant. And so this would be, my delta N here would be 2 minus 1 plus 1, which is 2. So in this case, my delta N is 0, so my Kp is also going to be 39. So that's a relationship just to have handy to know the difference between Kp and Kc and how to toggle between them. All right, the fourth one is I want to find equilibrium concentrations. But I'm given here, now I'm given my equilibrium constant and one equilibrium concentration. So let's go back to our trusty A plus B to C, KEQ, and all but one equilibrium concentration. And I'm going to be given a KEQ value. So here we'll say this is 11.8. This is 0.10 molar. This is 0.33 molar. And this I don't know. So this is also a very simple case here, because all I need to do is, one, I'm going to write my mass action. So my mass action for this is KEQ equals C squared over AB. And then 2, I'm going to plug in and solve for my unknown. My unknown in this case is going to be this guy. All right, so my KEQ is 11.8. I don't know C, so I'm just going to assign that X. And then I'm looking for, well, we'll call that C, just so we don't confuse. I'm looking for 0.10 and 0.33 molar. Okay, so I'm going to multiply these together, then I'm going to multiply it by 11.8. My concentration of C, so here I'll write this out. So this would be 11.8 times 0.10 times 0.33 equals concentration of C, because all of this is going to take the square root of it. That means C is 0.62 molar. Right, so that is the fourth way, and the fifth way is our more complicated way. The fifth way is going to require an entire sheet of paper here. Is I want to find my equilibrium concentrations, and these are the pieces that I'm given. I'm given initial concentrations of all substances and KEQ. So what I'm not given, any equilibrium concentrations. This is going to make it hard. This is my difficult problem, that my equilibrium constant is 25, and then my initial concentrations are this. So now I'm given initial concentrations of everything, and so the assumption that I can't make here is that my reaction is necessarily going forward, because what I've done is I've taken A, B, and C, I've mixed them all together. So I don't know if the reaction is going forward or going backwards. And so the fact that I'm given here an initial concentration of a product, I need to find Q and reaction direction first. If this was 0, then I wouldn't need to do this step. But since it is, and I'm going to do this step, so first thing is I'm going to find Q. And I'm going to write Q as it's given. So Q here is going to be equal to C squared over A plus B. And so if Q is less than K, then the reaction is going forward, meaning it's still going this direction, and I can use this equation as I've written it. If Q is greater than K, then the reaction is going in reverse, and I'll need to reverse this reaction before I write my mass law. So I'm going to plug in my initial values here, find Q using initial concentrations. So Q here is equal to 0.50 squared over 0.82 times 0.82. And in this case, I get a Q of 0.377. So Q is less than K. So I know that my reaction is good in the direction that I've written it. This tells me that I can use the reaction as written. And we'll come back and we'll do an example where I have to flip everything. Okay, so this was a whole waste of my time. Not really, but now I'm going to forget everything I did here, because once I get here, that's all I need to know for this. So now we'll call this 1A. Now I'm going to do 1B. I'm going to write my mass action. Now that I know that the reaction is moving forward initially, I'm going to write an ice table as my second step. So I'm going to rewrite my equation here. I'm going to have an initial, I'm going to have a change, and I'm going to have an equilibrium. So my initial concentrations are 0.82, 0.82, and 0.50. And that was in my initial set of conditions here that I gave myself. Now I'm going to look at what my changes are. So this is going to go down by 1. This is going to go down by the same amount, and this is going to go up by 2 times that amount. And this is all coming from the stoichiometry. This is a 1 to 1 to 2. So this is for every one of these is going to react, and 2 of these are going to be made. So that means my equilibrium concentration for A is going to be 0.82 minus whatever X is. B is going to be 0.82 minus X, and 2C is going to be 0.50 plus 2x. Now I'm going to take these values and I'm going to plug them back into my mass action. So step 3, I'm going to take my equilibrium values, equations really, into my mass action. All right, so KEQ, if you remember all the way back here, was 25. So I'm going to have 25 equals 0.50 plus 2x, and this whole thing is squared, over 0.82 minus x times 0.82 minus x. Now I'm going to solve for x. This is a lot of quadratic equation stuff here. If I have something, I'm going to give you a thing to look out for. It doesn't always happen, but it will occasionally. If these are the same, I can rewrite this here this way, 0.82 minus x squared. These mean the same thing. If I break this out, this is what this means. So that means that if I take this down, and I'm going to use this down here, and say 25 equals 0.50 plus 2x squared over 0.82 minus x squared, I can actually take this square out and put it to this whole thing. Both of these are squared, then I can take the division of this and then I can square it. I want to get rid of this square, so I'm going to take this over here and take the square root of 25. And that's going to allow me to get rid of that square, and it's also going to allow me to avoid the quadratic equation. And I can only do this because these were the same down here. So if these were different, I would have to solve this whole thing. But since these were the same, I could do this little shortcut here, bring it down in here, get rid of the 2, take the square root of this. So when I work this out, I'm going to get a value here of x equals 0.514. I'm not done yet. Okay, all I've done is solve for x at this point. So now I need to go back up, because remember, my original thing is I'm looking for the equilibrium concentration of all the substances. So I'm going to take this, I'm going to go back to my ice table, and I'm going to find my equilibrium concentrations. So this one here, and these are going to be the same. So this is going to be 0.82 minus 0.514, and that's going to give me 0.31. So this is going to be the same. And then this is going to be 0.5 plus 2 times 0.514. And that's going to give me a value of 1.0 molar. So if I've done this right, this is going to go down, right? These are going to go down, and this is going to go up. And I'm just going to check just to make sure. 0.82 is what I initially started with. I ended up with 0.31, so that one went down. Same here. And I started with 0.5. I expect that to go up, and it did. It went up to 0.1. So this would be my answer here. This is my equilibrium concentration of A. This is my equilibrium concentration of B. And this is my equilibrium concentration of C. Let's go back to this original scenario here, and let's see what would happen if Q was actually greater than K. So this one we had Q was less than K, meaning that the reaction is still, even though I have C present at the beginning, the reaction is still going forward, so I can write my KEQ as I have it written. So let's assume that I don't have that. If Q is greater than K, now I have a problem. So I'm going to rewrite my equation. And now I'm going to give you some different values. KEQ is still we're going to let that guy stay at 25. But now I'm going to give you some different initial concentrations. So let's say A initial is 0.25 molar. B initial is 0.25 molar, and C initial is 1.0 molar. So now, since I have also, here I have given initial concentration of C, I need to, which is my product, I need to find Q and relate to K to find direction of reaction. To find Q, same way, I'm going to use all my initial concentrations. I'm going to write it like a mass action. I'm going to plug in my initial values though, and this is going to give me, actually sorry, this is 1.6. A Q value of 40.96. And this is important because now Q is greater than K, so my reaction is proceeding in reverse. So now I did all this just so that I could figure out how my reaction's going. It's actually going in reverse, so I'm going to rewrite my reaction in the direction that it's proceeding. Now I'm going to go through my steps. I'm going to write my mass action. So my mass action for this is, because now my reaction's going in the reverse, so this is going to be reversed. I'm going to write my ice table. So I'm going to write my initial concentrations. My change is this is going to lose 2 times, because it's proceeding this way, so this is going to lose, and these are going to gain. My equilibrium concentrations, this is going to be 1.6 minus 2x. This is going to be 0.25 plus x, 0.25 plus x. I'm going to plug those into my mass action and solve for x. KEQ is now going to be equal to 0.25 plus x, and I have 2 of them, so I'm just going to square that, over 1.6 minus 2x squared. And so now I can do the same thing that I did before, where I can get rid of these squares by taking the square root of K equilibrium. And this, remember, was 25. That was given. And so when I solve for x now, I'm going to get 0.268. Now I'm going to take this value, go back up into here, and find my equilibrium concentrations. So C at equilibrium is going to be 1.6 minus 2 times 268. And that is going to be 1.1 molar. So it went down. It went from 1.6 to 1.1. And both of these are going to be the same, 0.25 plus 0.268. These are going to be 0.52 molar. So those are my equilibrium concentrations for all of the substances that are in this reaction. So those are the 5 ways to do the problems in this chapter. Now, I know you would like to have another shortcut, because shortcuts are good. Everybody likes shortcuts. And so there is a shortcut that you can use. You can only use it if you have certain conditions that are there. And this is called the XSmall Approximation. In the XSmall approximation, when the equilibrium constant is very small, so we're talking about 10 to the minus 3, 10 to the minus 4, and the concentration is relatively high. So your concentration, your initial concentrations of your reactants are initially high, then you can do this XSmall approximation. But once you do it, you have to go back and check. All right, so let's say I have even a simpler reaction here. A goes to B. Can I use the X is small approximation? And I'll explain what that means. This happens when you have KEQ is very small. So first condition, my KEQ is very small. So we're talking 10 to the minus 3, 10 to the minus 4, etc. So things that have really small KEQs. And the second condition is that you have high initial concentrations of your reactants. And the reason that you can do this XSmall approximation with these conditions is if KEQ is really small. So let's say here that my KEQ is 3.3 times 10 to the minus 5th. What this tells me is this is so small that it tells me that this appreciably isn't going to change very much. I'm favoring reactants, I'm not favoring products. And so this is not going to produce a whole lot of products. So the majority of what's going to be in the solution at equilibrium is still going to be A. So that's condition number 1. Condition number 2 is I have to have initial concentrations that are really high. So A, let's say A initial is 1 molar, and then I don't have any of my product when I start out. This is high if this is my equilibrium constant. This is really high. So I'm going to solve this 2 ways. Okay, I'm going to solve this using my XSmall approximation and show you what that means. So A goes to 2B. I'm going to set up my ice table here. This is 1 molar. This is 0. My change here is this is going to go down. This is going to go up by 2x. My equilibrium concentration here is going to be 1 minus x. Here it's going to be just 2x. So that x, remember, x is the amount of concentration change. That's how much of A is going to be converted into B. If A is really high in concentration, I'm probably not even going to appreciably within significant figures see this change in x. And so if this and this are on the order of 10 to the 3 apart, then I can use my XSmall approximation. If I'm not sure, I'll use it and then I'll go back and check. So I'm going to write my law of mass action. I'm going to do everything the same in the beginning. I did my ice table. I'm going to write my law of mass action, B squared over A. Now I'm going to take my values and plug them in. So KEQ was 10 to the minus 5th. B, that's going to be 2x squared over 1.0 minus x. So my XSmall approximation, if I start with 0 concentration of B, B is going to go up. I'm going to have a concentration of B. So I can't do anything with this x. But my XSmall approximation is saying that this is going to be so small that when I subtract it from 1 molar, it's essentially still going to be 1 molar. So this is not going to change appreciably. This is going to change. So I'm going to leave my x up here. But this just allows me to remove this x only. So this is the x that's reducing the concentration of my reactant. That x I can remove. And when I do that, what you see is that it greatly simplifies this equation. So now my equation is going to be 3.3 times 10 to the minus 5th equals 2x squared over 1, essentially. Now I don't have to do a quadratic equation, which is really nice. So this would be 3.3 times 10 to the minus 5th equals 4x squared. and x is going to be 0.0029. This is be my change in concentration. I want to check my assumption. So I could plug this in. Before I worry about finding my equilibrium concentrations, I'm going to check this. My assumption here is that this is so small it's not going to appreciably change this, which it is really small, but I'm going to do a calculation that allows me to be comfortable with this. I'm going to compare it to my initial concentration. So I'm going to take my value for x, I'm going to divide it by my initial concentration, and I'm going to multiply that whole thing by 100. If this percentage here that I get out, if this is less than 5%, then my XSmall approximation is okay. That means that I can use it. If it's greater than 5% here, then I can't do this and I have to go back and solve this as a quadratic equation. I can't remove the x here. So this is going to allow me to check to make sure that I could. So I'm going to take my 0.0029, I'm going to divide it by 1 molar because that was my initial concentration of A, and then I'm going to multiply this whole thing by 100, and that's going to give me 0.29%, which is less than 5. So that means that my XSmall approximation was okay. Now I'm going to go back up and figure in my equilibrium concentrations. So that's my equilibrium concentration of my product, which is really small, which I would expect because I have a really small equilibrium constant. So in this case, if I have these conditions here, I can use that XSmall approximation. The only place I can remove the x is here from where I'm subtracting it from the reactant. I can't remove the x here. And then I want to kind of come back at the end and make sure I check my XSmall approximation, and I'm going to do that here. As a rule of thumb, if I look at my initial concentration and my equilibrium value here, and if these are 10 to the third apart from each other, then my XSmall approximation is going to work, meaning that this, if I wrote this in scientific notation, this would be 1.0 times 10 to the 0. And so 10 to the 0 and 10 to the 5th are more than 10 to the 3rd apart, so then I know my XSmall approximation is going to be good. If my A value, if this here was instead 0.01 molar, now I'm going to be iffy because this is not very large. And so if I convert this to scientific notation, this would be 1.0 times 10 to the minus 2. I'm still 10 to the 3rd apart, so it might be okay. I might still be concentrated enough to where I can use my XSmall approximation, but I'm right on that cusp, so I'm probably going to check them. If my initial concentration was instead 0.001 molar, and that would be 10 times 10 to the minus 3rd. Now I'm 10 to the 2nd apart, and I can't use my approximation anymore. So that's kind of your rule of thumb. If you put this in scientific notation and you're 10 to the 3rd different between your initial concentration and your equilibrium constant, then you can use that XSmall approximation. Okay, so I think I'm going to stop here and break this part 3 into 2 parts. In the next little bit, we will come back and we will talk about stressors that we can do to an equilibrium system.